In this video, we'll talk about ways to secure REST API. There are three things when it comes to web security: authentication, authorization, and connection security. Authentication is a process of establishing the identity of a client. Typically, it involves asking the client for username and password. The server will check the username and password, and if they match the ones on record, the server knows who the client is. Note that even though a client is authenticated, it doesn't mean the client can access everything. The server usually needs to do another check and see if the client has a privilege to access certain resource. This process is called authorization or access control. And because the client and the server communicate over the web, and because the web is full of bad people, we must ensure the connection is secure. So if someone is eavesdropping on the network, they won't get private information like your password or credit card number. Connection security is something outside applications, so we won't spend too much time on this. Usually it's covered in a networking class or a security class. For us, just know that we need to use HTTPS to ensure connection security. To use HTTPS, you first need a so-called certificate. You can create one yourself called a self-signed certificate. Self-signed certificates are fine for development and for behind-the-scene usage, like for communication between backend services. But browsers don't consider them valid certificates. So if you use them on a public server, you'll scare your customers away. These days, you can get free certificates from the organization called Let's Encrypt. But you'll have to be the actual owner of a domain to do that. For example, I won't be able to get a certificate for a Cal State LA server because I don't own the Cal State LA domain. Once you have a certificate, you can then configure HTTPS on your web server or on the embedded Tomcat server in a Spring Boot application. So now let's assume our connection is secure. What do we need to do in our applications? Well, security is really a very complex thing. Here we'll discuss a basic scenario and use it to discuss some fundamentals in web application security. Here in this scenario, we'll have an application that manages its own user credentials. For example, having a users table in a database. The authentication will ask a client for username and password, and login here could be a login page in a web application or a login endpoint in a web API. After a client is authenticated, it may try to access protected resources, and the application needs to check whether the client is authorized to do so. So this is a fairly basic setup, but there are a few important questions we have to answer. First is how to store passwords safely, and this applies to both web applications and web API. The next two questions are kind of related. What happens if authentication is successful, and how do we check subsequent requests? The answer to the first question is, instead of storing user passwords directly, we should run them through a cryptographic hash function and store the hashed password or password hash. For example, if the original password is ABCD, we would store something like this instead of ABCD. This, of course, raises some questions of its own. The first is, why do we want to do this? Why not just store the original password? The obvious answer here is that we don't want anybody to see users' passwords, even the system administrators. But there's also a less obvious reason. Users tend to reuse their passwords on different websites and services. If an attacker breaks into one system and steals the user passwords, they can try the same passwords on other systems. This is why we should only store password hash, so that even if our system is compromised, the attacker cannot get the user's passwords to hack the user's other accounts. So at this point, you may be wondering what's the difference between encryption and hashing, as they sound pretty similar. The short answer is encryption is reversible, meaning you can take something, encrypt it, then later decrypt it to get the original. Hashing, on the other hand, is one way, meaning that in theory, you should never be able to get the original back. So you may be asking then, if I can never get back the original password, how can I check if a password is correct? Well, it's actually quite simple. You just need to run the password through the same hash function, then check if the result matches the hash value stored in the database. Just hashing the passwords is not quite enough, as hashed passwords may still be revealed by attacks such as brute force attack or dictionary attack or some combination of the two. Usually, an application should do more to make password hash safer, and this may include enforcing some password policy, for example, forcing users to use long passwords with special characters. It's also important to choose good password hashing algorithms. The current recommendations are Argon2, PBKDF2, scrypt, and bcrypt. You should avoid using algorithms like MD5 or SHA, which have already been proven to be bad for password hashing purpose. One more important thing is to use sort. Sort is just a piece of random data generated for each user. Sort will be concatenated with the user's password to produce a hash. Having sort makes dictionary attack a lot harder. Without sort, you can pre-hash a bunch of common passwords and use it as a dictionary to go from hash back to password. But with sort, the dictionary has to be exponentially larger because one password now has many variations when it's concatenated with different sorts. These days, I like to use bcrypt for password hashing. This is what a bcrypt hash of the string ABCD looks like. Note that this hash contains not just a hash value here, but also some additional information, like the version of the bcrypt algorithm used to create the hash, and the so-called cost factor, which you can adjust to make the algorithm run faster or slower. Generally speaking, you don't want the algorithm to run too fast, because then it will be easier to crack passwords by brute force. But you also don't want it to run too slow, because then checking password would take too long. Right now, I think 10 to 12 is a recommended range for the cost parameter. Note that sort is also included in the hash, which is nice because you don't have to use a separate column in your database to store sort. The library I would recommend for doing bcrypt hashing in Java is bcrypt password encoder from the Spring Security project. They also have password encoders for many other algorithms like scrypt, PBKDF2, and so on. If you want a standalone library, you can use jbcrypt. Okay, so now we know how to store passwords and how to verify passwords. Let's talk about what happens next. If you remember, in CS3220, when we program web applications, we use session-based security, which works like this. When a user tries to log in, the user will send us their username and password. we use that to load user information from the database and verify username and passwords. If authentication is successful, we save the user information in session and we return a session ID back to the client. The session ID will be included in subsequent requests, and the server will use the session ID to look up the user information in session. And once the server finds the user information in session, it can use it to determine A, if the user is already authenticated, and B, if the user can access the requested resource. There are some advantages to implement security this way. The most important one is actually efficiency. Because session data is kept in memory, when a request comes in, it's very efficient to check if the client is already authenticated and whether the client is allowed to access some resource. Another benefit is that it's easy to revoke access. If you don't want a client to access the server anymore, you'll just need to remove the session data for the client from memory by doing a session invalidate, and that's it. But there are also problems of using session. First, session data takes up server resources, and will have lots of users. That's already a big problem by itself. To make matters worse, because session data is kept in the memory of the web server, it also makes it difficult to do the so-called horizontal scaling. When your web application or web API is under heavy traffic and you want to increase its capacity, you can do two things. You can get a bigger server with more memory, faster hard drive, more CPU cores, and so on, and that's called vertical scaling. The problem of vertical scaling is that you reach the limit of a single computer very quickly. Very soon you'll find out that there's just no faster CPU you can buy or no more memory you can plug onto the same motherboard. On the other hand, you can try horizontal scaling, basically adding more servers. You can put a load balancer in front of the servers to distribute the traffic to those servers. There's almost no limit on how many servers you can add. So this is a much more effective way to scale. Except for one thing. If you use session data is kept in the memory of one server. So all subsequent requests from the same client will have to go to the same server, regardless of how many other servers you have available. Very soon you'll find that the load is no longer balanced. You'll have some servers that are very busy and some servers underutilized. Session-based security is fine for web applications without too much traffic. But for REST API, we need to come up with something that does not require session. Remember, one of the REST constraints is stateless, which basically means no session. And this is crucial for the efficiency and scalability of the system. But this is not the only requirement for a security mechanism. We also need to consider access control, access expiration, and revocation. So how can we do this without session? The answer is yes, we can, and it works like this. A client will first try to authenticate with a server by sending username and password, just like before. And if authentication is successful, the server sends back an access token. The access token will be included in subsequent requests, and the server can use the access token to determine if the client is authenticated, and if it is, whether the client can access the resource. Now, if you look at this, and you compare this to this one, you may be thinking that they don't look too different. This one, for example, sends back a session ID, and this one, for example, sends back an access token. So what's really the difference? Well, the trick is inside the access token. The difference is that now the user information is actually included in the access token itself instead of being stored in session data on the server. In other words, the user information used to be stored here on the server, and now is in the access token itself. In particular, the access token itself may contain information like the name of the user and the access privilege of the user and so on. Now, this is great because just like before, we don't need to go back to the database to load user information in subsequent requests because user information is already in access token, and every time a request comes in, we just need to examine the access token and we get all the user information from there. Now, you may be saying, wait a minute, how can this be secure, right? In the session case, the user information never leaves the server, so nobody can change the user information. But in this case, the user information is in this access token sent back to the client. So the client could change the access token, for example, changing isAdmin from false to true to make a client administrator itself. How can we prevent that? Well, that's why we have cryptography. There are, in fact, two ways to prevent a client from tampering with an access token. We can encrypt the token, and because only server has the encryption key, the client cannot do anything with the token. In fact, in this case, the client cannot even see what's inside the token. And that may actually not be desirable in some cases. For example, sometimes after a user logs in, the client may want to display something like hello John or hello first name of the user or something. So if we want to support that, we can take the second approach. Instead of encrypting the access token, we can sign it. There are many ways to sign something cryptographically. For example, you can use public key, private key, or you can even sign it using a cryptographic hash function like what we do with passwords. For example, we can simply concatenate the user information with a secret string that only the server knows. Because the client doesn't know the secret string, it won't be able to produce a valid signature if it changes the user information. So based on this idea, people came up with many different formats for access tokens. A widely used format is called JSON Web Token, or JWT. A JWT token has three parts: header, payload, and signature. Note that the whole token is encoded using base 64 URL. So when you actually look at a token inside a request or response, it doesn't look like this, it looks like this. However, know that encoding is not encryption, meaning that if you know the encoding method, you can easily convert it back to the original form without knowing some secret key. JWT token is encoded in base 64 URL, so the token will only consist of characters that are safe for URL. This allows us to send JWT as a request parameter in URL if necessary. For the JWT header part, as we can see, it's a JSON object. The header specifies the token type and the cryptographic hashing function used for the signature. By the way, JWT uses a signature approach for the token instead of the encryption approach. The payload is also a JSON object. This is where the user information is, and the user information included here are usually called claims. A claim represents a property of a user. For example, we can have an email claim which has a value jdo at localhost.localdomain, and we can have a given name claim with a value John, and so on. There are a number of predefined claim types. Here, for example, this payload has three claims. For whatever reason, I cannot scroll up. Yes. It has sub, name, and IAT. Sub and IAT are actually two predefined claims. Sub stands for subject. This is usually the user ID, and IAT stands for issued at. This is a timestamp when the access token is issued, of course. And there are a number of other predefined tokens. Name, in fact, is a predefined claim, not token, but sorry. It's a predefined claim representing the full name, and you have given name representing first name, family name for surname or last names, and so on. But very importantly, you are also free to come up with your own claim types. For example, if your system has admin users and non-admin users, you can have a claim type that says is admin, which could be either true or false. As you can imagine, you can implement access control based on claims. For example, you can allow a user to do something if the user has a is admin claim, or if the user has an IP address claim with a certain IP address value. And then the signature part, which is really just a hash value of the concatenated header and payload and a secret key that only the server knows. So knowing what we know, it shouldn't be difficult to implement security based on JWT. For the authentication part, after we get the username and password, we load the user information from database and verify the password. If authentication is successful, we create a JWT token and send it back. The commonly used JWT library is called Java JWT or JWT. So this one. And remember, when you create the JWT token, you need to put in the necessary claims, so later on you can use the JWT for authorization. And in subsequent requests, we can extract the JWT token from the request. The most common way to send JWT token is using the authorization request header. The value of the header will be bearer followed by the token itself. Bearer means this token is a bearer token, meaning that the token itself is enough for access control, no other information needed. Depending on the client, the token could also be sent in as a cookie or a request parameter. Once you get the cookie from the request, you should first verify the signature, and of course the library has a method for that. And if the signature is valid, you can grant access based on the claims in the JWT without needing to access the database. So it's quite efficient. You can implement JWT-based security with just the Java JWT library. But Spring does have some features that make implementation easier. In particular, if you want to extract the token from request in a controller method, you can use one of these annotations on a controller method parameter. For example, if the JWT token comes in as an authorization header, and if you have a method called foo, and you can do request header authorization. So this would extract the value of the authorization header and put it in a string token, which your controller method can access directly. By the way, usually the value of the authorization header also include the bearer part. So once you get the token, you need to do a substring to remove bearer space to get the actual token. But that should be fairly easy. And similarly, if the token comes in as a cookie or comes in as a request parameter, you can use these annotations to easily extract the token. But besides this, there are two Spring features that actually let you to move JWT code completely out of your controller. So you don't actually need to do this in your controller methods. The first thing you can use is filter. A servlet filter can intercept a request before it gets to controllers. So you can set up a filter here, and the request will first get to the filter, and then the filter can process the request, attach some additional data to a request, and then pass the request onto the controllers. You could also shortcut the request, meaning that you simply send back a response inside the filter without passing the request to the controllers. The servlet specification specifies servlet filters. So without using Spring, you can have filters in a Java web application. Spring has its own filters, which are essentially the same as servlet filters, except that Spring filters are Spring beans, which means you can do dependency injection and so on. So if you use filter, it's better to use a Spring filter that has more capability and configuration flexibility. So as you can see, filter is a great place to do some authentication and authorization work. For example, you can process JWT token inside a filter, and you can convert it into a user object and pass it on to controllers. And if the token is missing or invalidated, this filter can simply send back a for one response without even going through the controllers. By the way, if you are familiar with other web frameworks like ASP.NET Core or Node.js Express, you can see that filter here is really the same as middleware in some other frameworks. In Java web applications, these are called filters. A similar way to using filters is to use Spring controller advice. We've seen how controller advice can be used for exception handling. They have another great usage. They can be used to create some objects that can be used by controller methods later. These controller advice methods are called model methods because they produce models which will later be used by controller methods. They are annotated with model attribute annotation, and in this example, the method creates one model object called current user. You can also create multiple model objects using a model map. In terms of JWT, we could put the JWT processing code here. If a JWT is present and valid, we can create a user object to be used later on by the controller methods. And if the JWT is missing or invalidated, this object could be null. To use that object in a controller method, we can add it as a method parameter with the model attribute annotation. This way, depending on the user information in this object, we can grant access or throw an exception saying the user has no access. Okay, so this is the end of this video. See you in the next one.